Thanks so much for the introduction, Joe. I am going to be talking about the management of context in the machine learning lifecycle. And so to give you an outline of the content that's going to be covered in this talk, we're going to start by talking about what is the machine learning lifecycle, specifically closing the loop in the machine learning lifecycle, or how engineers operationalize machine learning, which is going to be work that's backed by an interview study. We're going to talk about context, whether it's the missing piece or what you would be able to do with it. And then kind of after giving an overview of what the machine learning lifecycle is, I'll go into my dissertation project, Floor, and talk about how I aim for it to fulfill the vision that we laid out earlier in a KDD workshop called, where we cover the ABCs of context. And Floor is a project that has been developed over the years, kind of in layers, starting with just application context with Floor, then adding change context or application and change context with FloorDB, and now finally kind of covering the whole ABCs of context with Floor Flow. So the very first thing that I'm going to cover is closing the loop and how engineers operationalize machine learning. So ML is the enabling technology behind decision-based applications and services. It appears in voice assistants, ChatGPT and LLMs in the current generation, self-driving cars, personalized medicine, and also document intelligence, which I'll have a couple examples of in this talk. Now, the machine learning lifecycle is a three-phase process consisting of building out a pipeline, running the pipeline to train a model, and then deploying the model out into production. You may see this in different flavors, like Amazon's SageMaker also adds monitoring, and MLflow covers around the same material, just in a finer grained detail. But in substance, it's all talking about the same thing. So zooming in a little bit into building model development is going to be iterative and empirical, where an ML engineer works with an offline snapshot of data. And they do some data cleaning, exploratory data analysis and visualization, model design, training and validation, and then they get a pipeline. But they're never really satisfied with the first thing they try. So they're going to try and try and try again. So to quote a participant from a recent interview study, they tell people will have principled stances or intuitions for why things should work, but the number one thing to do is achieve scary high experimentation velocity. So we're going to take this training pipeline and then we're going to train on it. And there's going to be two things that are distinctly important about the training phase. The first is that you are going to be retraining automatically on a cadence. You don't need to worry about models going stale if you're retraining it daily. And also the amount of the three V's of big data, the volume and velocity of data. It takes exponentially more data to keep getting linear increases in performance. So you're going to train, you're going to tune the parameters of this pipeline, and then at the end, you're going to get models. And those models are going to get deployed so that an on-call MLE monitors those deployments in production, ensuring quality at scale. So those models are going to get connected, the predictions are going to get consumed by downstream models, and then an end user application is going to query the prediction service and get predictions in return. And Emily tells us we don't have a good idea of how models will behave in production until production. So they have to kind of always be monitoring, always be on the look. Then some feedback is going to work its way back into training, into training the models, adjusting the validation sets. And so in the end, to recap, this is the machine learning lifecycle. This is what I'm going to be talking about. There's some feedback from deploying to training, and then also some higher level feedback into building. So sometimes you also rework those pipelines. And so we did an interview study to understand this work, where we spoke to 18 ML engineers over the course of a year, and we used grounded theory methods, specifically constant comparative analysis and open and exfil coding for some of these results. And so the quotes that I've been presenting throughout the talk are drawn from this paper. It's great work that we did together with Shreya. And so if you're interested, I refer you to the paper, which will appear in CSCW this year. Now, closing the loop is going to be easier said than done. I'm going to have some like phrases to help us, almost mnemonics to help us remember, like what are some of the challenges about closing the loop, and then back those mnemonics with like findings from the interview study. So, and Emily tells us that the data set is supposed to have data for 50 states, but they only find 40 states. So where did the other 10 go? This data looks wrong. Feedback is always delayed at least 2 weeks. So when we realize maybe something went wrong, it could have been 2 weeks ago. The feedback could arrive late. If a new model's performance drops and an older model is still performing within a valid range, we roll back and just cut the losses. It worked better yesterday. And you have to bridge the gap between what's often a subject matter expert in one room, annotating and then handing things over the wire to a data scientist, a scene where you have no communication. I fixed it. Who needs to know? And we have some filters we keep around so we don't break something, but we're not so sure what they do. Filters can accumulate over time into pipeline jungles. Like they don't work here anymore. So having covered some of the challenges of closing the loop, we're next going to talk about context and the importance of it. So I'm going to introduce Floor, which is my dissertation project. Floor is a system to capture and manage context throughout the machine learning lifecycle. So next, I'm going to walk through a sample model training script where we import libraries and set hyperparameters. And then for each epoch and batch of data, we split the batch into data and labels, reset the optimizer gradients, run model prediction on the data, calculate the loss, backpropagate the gradients, update the model weights, and then log the loss. At the end, we evaluate the model's accuracy. And so in order to talk about context, I'm going to refer back to a paper from Joe, Vikram, and Joey, as well as other co-authors, called Ground, a data context service. And something that really interested me about this work was that it involved cooperation with people in industry like Trifacta, Capital One, Cloudera, and LinkedIn. And they talked about some of the real world problems that they encountered because of the absence of context or the absence of data context. And there's also like, especially if people starting in the PhD, like I highly recommend to go and look at this paper. It's full of great ideas that really stood out to me early on. Like one of them is Postel's theorem: be conservative in what you do, be liberal in what you accept from others. And so the system presents Ground, the data context service. And so I wanted to work on something like Ground, but for the machine learning lifecycle. And so that's why we called it Floor. It kind of like phonetically, it kind of sounds like a floor, like tile, but it also sprouts from Ground. And then we published this paper in a KDD workshop called Context, the Missing Piece in the Machine Learning Lifecycle, where we talked about like, well, we want to talk about, you know, this missing context in this scope, like what would it be like to have the context that's missing? So putting that aside and then stepping in to Floor and the ABCs of context, we're going to start with the first like core chapter of my dissertation. So the ABCs of context is rich metadata. It's when you usually think about metadata, like describing some data set, like a schema, you're usually thinking about application context. You can also think about build context, which is like lineage or provenance. Where did this come from? Where does it go? And change context, or how does it evolve over time? So returning to this example, application context is core information that describes how raw bits get interpreted for use. The value and meaning of expressions at runtime are like what application context is. And so anything that could be logged is fair game. Now, very early on, we saw that you could always log more data. And you could ask about the hyperparameters, and that's going to be like some context that kind of describes the training application. You could also, in addition to logging the accuracy, you could log the recall. But even if you were to log everything, you wouldn't catch all that you need. Like if you wanted to get the tensor histograms, there was no logic in that training script for you to extract it. So there's almost like, once you start considering derived data that you can get from expressions, this application context becomes potentially infinite. And so the idea here, the intuition was to allow the MLE to ask for the information that they need post hoc, after execution, and then to use record replay techniques to recover the data that they need efficiently. And so that was the subject of study in the hindsight logging for model training paper, which appears in VLDB 2021. So let's go into an example of what hindsight logging kind of looks like, or a motivating scenario where you have a model training script that runs on a GPU, and then you see some loss curves. So like, how well is the model training? And, you know, this is a story from a graduate student that they say, this seems off, the loss curves don't look right. So like, I need to look at the tensor histograms. And then they go back into the code, they add the additional logging statements, and then they rerun training to get the information that they need. The issue here is that deep learning training is so time consuming that to do this naively is kind of prohibitive. So the challenge here is, if we already ran something for 7 hours, what do we need to do, you know, computer science wise with our techniques in order to bring down those 7 hours to 2 minutes? The approach is going to be fast recovery from checkpoints. So remember those 2 passes, that's going to be record and replay. During record, we will want selective checkpointing. Balance replay latency and checkpointing overhead with physiological logging. Or physical logging, we checkpoint models to disk, and logical, we're saving code so that we can recover state from checkpoint. And then we're going to move logging overhead off the critical path using fork one-shot, one-way IPC. In fast replay, we will do the least work necessary. So this is going to be skipping irrelevant code, which is program slicing, and not duplicating work, which is memoization. And then we want to do that least work in parallel. And the finding is that even sequential training code can be parallelized on replay, given checkpoints. So let's step into background logging and checkpointing. Logging and checkpointing consists of serialization followed by a disk write. The expensive part here is going to be the serialization. And so a noise level trick is to copy memory using copy on write with fork, and then have the child process be the one that does serialization so that it's not something that you're blocking on during the execution. This is the subject of study of Eric Liu, so before I step into that, let me very quickly say that we took some measurements and we were able to cut the materialization overhead by 74% on average, which allows us to checkpoint with higher frequency than otherwise would be normal. And so this was a subject of study of Eric Liu, who completed a master's thesis at Berkeley, studying and helping with the floor project. So the thing with record is that we don't want to add a lot of overhead. These are long-running jobs. We have some examples that are fine-tuning, and then other examples that range from 15 to 20 hours. Periodic checkpointing is checkpointing once every epoch. So this is something that you would do manually. And it's okay for like some Wikipedia model training or Jasper, which is an NLP model. But for the recognizing textual entailment, COLA, CIFAR, like the fine-tuning cases, we see that the overhead can be almost a 2x. And so if you're going from like 30 minutes to an hour, that's a problem. If people turn floor off, then you kind of lose all the benefits. So you need to make sure that you're keeping those overhead bounds very tight. And so we are going to use adaptive checkpointing. So we're going to be taking measurements of how long each loop takes. And then we also know the size of the model. We know how long it takes to write. And so we kind of like balance how long it would take to write, how long it would take, how much speed up we would get from replay. And then that's how we automatically decide to checkpoint. And the thing also that's helpful here is that we can choose our overhead. We can tune it. So it's 6% by default, but we can ask for a lower overhead if that's necessary. So during record, we take checkpoints, and then those checkpoints are used to parallelize and reduce the latency. So for the intuition for parallel replay of model training, we have this same example that we've been covering. During record, the GPU is stepping sequentially through the instructions in the nested loop. At replay time, we can add GPUs, and then each GPU can load from checkpoint and perform its set of work. Now, every epoch is replayed in parallel, and this is something that we can auto-parallelize for model training replay. So let's talk about some of the speedups that we get. If we have a single instance with a single GPU on one of the benchmark examples, it takes 400 minutes to train, and it costs about $20.20 in the cloud. Now, what do you think happens if I add 4 GPUs? I'm going to get something very close to ideal speedup, down to 100 minutes, but the cost is not going to go up. That's because I'm not leasing the GPU for as long as I was before. And this trend is going to continue as I continue to add instances or I continue to add GPUs. To quote Benoit from Snowflake, in the cloud, fast is free. So the approach again for hindsight logging is going to be selective checkpointing, so low overhead record, and then fast replay. And we cover all of this in detail in the paper. So if you're interested, I invite you to refer to the paper. So we finished talking about application context with Floor. And now we're going to talk about change context with FloorDB. As a recap, change context is change over time, evolutions, or version histories. This is information about the version history of data, code, configuration parameters, and more, including changes over time to both structure and content. This work is published in archive in FloorDB multi-version hindsight logging for continuous training. And so a good way to understand why we care about change context is through the following scenario, which is continuous training. So here, Alice is an Emily working at a self-driving car company. And her task is to improve performance on roundabouts. So they're going to be shipping in a new country, and that country has more roundabouts than we do in the US. So this is something that she has to do. The average loss and the F1 score, the black and green lines that you see on the screen, are just going to be like training metrics, and they fluctuate as data comes in. It kind of keeps them within some valid threshold. But the F1 roundabout, which is the red line, is the one that she is intentionally optimizing. And so that very quickly spikes up, and then she holds it up. So she's doing really well because she's improving the F1 score for roundabouts without hurting global metrics. But a colleague tells her that they've lost the ability to detect pedestrians. And then when she goes back and looks in the data, she realizes that none of the roundabout photos had pedestrians. And so it's like, oh, well, that's why. So her question is, when did I lose the ability to detect pedestrians? That information is not in the metrics that she logged. And look at how this is like, the latest one is in September, and it goes as far back as March. So she's going to need to add a new logging statement in order to get that information, and she's going to have to like reach back in history. Further problem is that the model training code in March probably looks very different from the model training code in September. So this is the first time that I'm showing you the Floor API, so I want to pause for a second and step in. We use Floor arguments and logs as a way of capturing some runtime values and making sure that those hit disk. Arg and log is transparent in the sense that it returns the value that it takes in. And so if you're using Floor with weights and biases or MLflow or any other system, this is the way that it's supposed to interoperate. It just kind of like intercepts some metadata, but it also allows it to pass through. And then we define the set of checkpoints as well as the checkpointing context, and those are controlled by Floor loops, which are going to, at iteration boundaries, decide whether to checkpoint or also like load a checkpoint state and then execute the instructions to recover the logging statements. Now, managing multiple versions. So we have all of these different versions that are changing. It's going to be necessary to auto commit to make sure that all of those executions are able to be recovered for hindsight logging. But anyone who has worked with like auto commit or version control knows that like auto commit is one of those things that solves a problem, but then also creates a problem. Like if you start auto committing Jupyter notebooks, like have fun. And so in addition, we can't just browse through the source code and see like how things are changing because it's not going to tell us that much information. We're going to need a relational model. And so in this relational model, I can ask for seed, learning rate, loss. Those are all things that I logged through like a floor arg or a floor loss. And each one is going to correspond to a column in the data frame. And so then I can kind of see how things are changing over time. To do floor replay, Alice is going to perform 3 steps. One is add the hindsight logging statement to the latest version of code. Just like open the VS Code or the code editor and add the logging statement. Then run a command from the command line where she calls Python floor and says replay F1 pedestrian is the name of the logging statement. It's the static identifier for the logging statement. And then she's going to say replay for anything from like June 23rd forward. So not for the whole history, just kind of like for the recent past. She's going to get a schedule. Remember how we're doing adaptive checkpointing. So those profiling statistics are also useful when it comes to estimating how long that replay is going to take. And so in this case, it's like a shorter example. It's like replay will take 10 seconds, and she confirms and moves on. And the way that that looks like is she has the metrics that she previously logged. She added the logging statement, she replays, and so the new metric then appears, and she can see, the catastrophic forgetting instance occurring sometime in July. And so she has time where she can roll back, so that she doesn't lose too much of the roundabout benefits. And so the FloorDB architecture is going to consist of a record component where the API reaches out to a serialization layer. So it's like Pickle, Cloud Pickle, that kind of serialization. And the large binary objects are going to hit an object store or some kind of cloud storage manager. And then the code is going to get versioned in Git. So we're going to use Git for version control. And we also talked about SQL, so the relational schema, in order to manage the metadata as it changes over time. And we added logging statement propagation. So this was the subject of study of Anusha's master's thesis in fast low overhead logging extending time. And so this is like a software patching technique. Like you have different versions of code over time. How do you adapt? First, you need to like identify the place where you inject the logging statement, and you need to adapt the logging statement to make sure that the logic matches out. And then at replay time, you're going to access those same submodules. There's going to be a pivoted view module for the floor data frame. And then there's the query parsing for floor replay, the empirical cost predictor that uses profiling statistics, and then a plan executor that calls Python sub-processes underneath. And so if you're interested in finding out more, this paper is the FloorDB multi-version hindsight logging. You can find it on arXiv. So now that we've talked about application and change context with FloorDB, we're going to move on to the final part of the talk and talk about, the full ABCs of context with FloorFlow. So build context, in addition, is going to be lineage or provenance or producer and consumer relations. Build context is information about how data was created and used. Dependency management for distribution and building across different machines and by different people. Provenance and lineage. Routes, pathways, or branches in pipelines. Flow of control and data. And this is the kind of flow that we talk about with Airflow and ML flow. And so if you think about ML flow and you try to think about like, is it a flower? Is it a system for flowing? Like, why don't people call it flowers? And so it's like everyone would immediately read it as flower. And so that's also floor, right? Like the flower for ML. Floor is going to be compatible, or Floor ships by default with SQLite for the SQL management, but it can also extend to support like Postgres or Oracle or whatever database someone chooses. Likewise, Floor ships with Make for the build management, for build context, but just as easily, it can also be extended to support Airflow or MLflow, like the tools that people prefer in their workflow. So in this particular scenario, it's a simple document intelligence case where we're doing document segmentation and text extraction. And the reason why I find this interesting is because it's a closed loop where a single developer is responsible for everything end to end, and the feedback is something that can be controlled. So you do inference on some documents, you see the kinds of inferences that the model is making, the text extraction of the OCR, the document segmentation across pages. And if there's a mistake, you can view that and correct it immediately. And then that cleaner data becomes training data for future rounds of training. So it's kind of like a closed loop so that we can study the ABCs of context. And so I'm going to talk about the build context for that application in this make file, where we define actions for processing a PDF, featurizing, which is extracting features from the text. That could be like the headings or the page number. Training a model on the features to extract or deploy a model that is used at inference for page segmentation, for text extraction. There's multiple models here. And then there's an alternative to that pathway, which is hand labeling, either through a script or through crowd workers like Amazon Mechanical Turk. And so at the end of this inference pipeline or this entire path, the model developer can run and view the web application. If that's not possible, they can switch paths and use the hand labeling instead. And so there's this tight feedback loop where the application can be opened, the model developer can review the results, and then they can make changes as needed. And then that improved data later feeds back into future rounds of training. So the Floor data frame was something that we designed to understand how things were changing in model training, but it's also something that we can use in multiple scenarios. So we can use it as a feature store. In this case, we are featurizing PDFs with Floor. And so we're going to define the Floor loop and the Floor page. So we're going to be iterating over documents. We're going to be iterating over pages. For each page, we can extract the text, extract headings, extract page numbers, or more. And so then the Floor data frame here looks kind of something like a feature store. Or if you have a feature store in your workflow, like this is how you would add Floor to also collect that data so that you also have that unified metadata. This data frame is going to have metadata such as the project ID, the timestamp and file name, the Floor loops, document and page, so what you're iterating over, and then the headings and so on. The Floor data frame can also be used for labeling data. So in the web application, when you're choosing what to show to the end user, you kind of have to choose a path. Like you could show model inferences, or you could show Mechanical Turk worker results. And so in this data frame, we see the same project ID, different timestamps. And so the file name is kind of indicating the different branch or the different path that was taken. We also have the Floor loop. And so even though we're accessing documents and pages in a completely different part of code, in a completely different part of the system, it's still very easy now to kind of join these data frames if we need to in our application. So we're still talking about documents and we're still talking about pages. So it's almost like lifting the level of abstraction. And then we have like first page or page color. And so you can convert from one into the other. And so then you're choosing what to display. You could display the latest thing, or you could display only something that's done by the model and so on. And then for the Floor data frame serving as the model registry, this is a case of, here I'm showing you inference code. And so we're first loading feature store at the beginning when we're saying features equals Floor data frame. And then later, we are loading the training data by asking for accuracy. And so we choose the model with the highest accuracy, and that's going to be the checkpoint that we're going to load for inference. And so what we're seeing is that the full ABCs of context fit inside the floor data frame. Application context is going to be something that grows wide. So remember, hindsight logging, you can always ask for more information, and it kind of depends on the use. It's not something that you can develop in advance. And so application context is going to extend sideways, and then build context and change context are going to grow tall. So this is something that the more you run, or the more you, instead of having a monolith script, you could kind of split it up for data flow. You could run something more and more times with version control. And so this is going to become a narrow gateway where you're taking metadata from all these different systems, all these different files, all these different parts, and then you're kind of bringing them in into a common layer, kind of bringing back Postel's law to be conservative in what you do and then be liberal in what you accept from others. So I'm going to be wrapping up my talk, but I will also be kind of revisiting like how I believe that the ABCs of context fulfill some of the needs in order to close the loop of the machine learning lifecycle. And so the first two cases of this data looks wrong or this feedback is late involve like change context, they involve build context. So if the data looks wrong, you want to see like, well, who changed it? What file did it come from? Can I roll back? The feedback being late, it's like, well, if you don't have feedback, you can't train the model. And if you can't train the model, like you need to get labeled data. And so you might need to go through a mechanical Turk crowd worker. So you want to keep track of that because the kind of mistakes that a mechanical Turk worker would make might be different from like feedback, which is like ground truth authoritative. So you want to keep track of that stuff. It worked better yesterday with the Alice example where you do a rollback. I fixed it, who needs to know? And so again, Floor is meant to interoperate with existing systems. So we build off of Make, we build off of Git. And when you're using Git, if different people have different repositories, if they own different sections or segments of the pipeline, then you kind of get some of the benefits from GitHub for free. So if someone has a Git repository for featureization and you fork that repository, then whenever someone makes a change to that, you're going to see how many commits behind you are of that. And so it kind of informs you to update. And then when they don't work here anymore, this is one of the cases where we're starting to extend that kind of like closed loop AI/ML development to include more and more people. And so this is having some people working on inference and UI, and then other people working on artificial intelligence only, and then kind of also interacting with some of the stakeholders who are like journalists or lawyers from NACDL and KQED. So, so far, this project has been about developing Floor. It's been about understanding the machine learning lifecycle, the ABCs of context, kind of like basing it off of first principles, almost like a top-down approach from Joe. And now that we have this project built out, kind of like from first principles, then the next step is really to like put it out in the wild, you know, like to get adoption, to get it using, see how much we can continue to stretch it, you know, as the organization grows, as we add people into the team, as we continue to move forward. So with that, I'm going to end my talk, say thank you very much to everyone, starting with my advisor, Joe Hellerstein, who has invested very much time and a lot of mentorship, and who has been exactly the advisor that I needed at every point in graduate school. And like the advisor that you need as like a first year is very different from someone who you need as like a 6th or 7th year. And so I think it just speaks to his experience, to his expertise, to have known how to be such a wonderful mentor. And also like a lot of respect and admiration for his ideas. I know that having studied some philosophy in undergrad, like moral philosophy, I was really drawn to virtue ethics of like, don't ask what you ought to do, ask yourself who you ought to be. And Joe is like a wonderful role model. I feel like if that's how I end up turning out as an academic, that would be like a life well lived. So definitely a lot of admiration for the kind of person that he is as an academic, as well as for his ideas. I also want to thank Joey Gonzalez and Kaushik Sen, who were mentors, especially in the early parts of graduate school. The ideas that I talk about with the machine learning lifecycle come a lot from Joey, from his kind of thinking, that kind of like practical real world, like something that's interesting. And so his mentorship was extremely valuable, and he was always very like motivating to continue to push in that direction. And then Kaushik, who is an expert in programming languages. So in the first chapter, we did some work with like automatically instrumenting work so that you could get record replay even if someone doesn't touch their code. Like ideas like that came from Kaushik. Also the logging statement propagation, where we're like injecting code and adapting logging statements, like all of that stuff is coming from Kaushik, so thank you so much. And then also Fernando Perez, another member of my committee, who I also have a lot of respect for his work as one of the creators of Jupyter and IPython. Like it's always kind of been so mysterious to me, like what's that? Like we know it's great, but like why is it so great? And like how do we replicate that success, you know? And like part of is it the feedback loop? Is it the fact that it's so agile? It's so like lightweight? Like so all of those things were definitely something that we kept an eye on as we were developing Floor. I also want to thank Shreya and Gabriel, PhD students who were amazing colleagues and that I learned so much from. Their help, their leadership also, it's just truly been wonderful to work with them. It's one of the benefits of coming to a school like Berkeley, is just having colleagues like that. And Aditya and Sarah also, who are co-authors in the papers. Thank you so much for your mentorship. I want to thank the undergraduate students, Pragya and Chitra, who were continuing to collaborate in some of the latest like court case processing cases, and master students, Eric and Anusha, who got master's theses working on projects based on Floor, and then their contributions later were folded into conference publications. Bobby Yan, who was an undergraduate student who is currently completing his PhD at Stanford. I want to thank senior PhD students who graduated already before me, but who it feels like standing on the shoulders of giants. I know that like Vikram was one of the chief architects of like context, ground, the ABCs of context. Dan was like working on Clipper towards deployment, towards later stages of the machine learning lifecycle, and Niraja, also like an excellent systems researcher who's now a professor at UT Austin. And countless other undergraduate students like Malhar, Karina, and Sona. So this is like great having access to work with the undergraduate students at Berkeley, who are, you know, excellent writers, and they're just star programmers, and also like really great people to work with. So I want to give thanks to the NSF and Dell for fellowship funding, as well as the numerous sponsors of the RISE and EPIC Lab, and I include some of the contact information for myself. So I'm going to hand it over to questions, but if people want a second to think, I can also move on to some personal acknowledgements.
Good question. First, wonderful talk. It's really awesome to see how far the project has progressed and how many details you took care of. It's really lovely. I have a question about something that I found interesting, but I'm curious about an assumption that I think is there. The approach you took to control latency and cost and impact, which I think is one of the things that makes it valuable, right, includes this idea of effectively parallelizing serial bottlenecks.
Yes.
Parallelizing through serial bottlenecks.
Yes.
And that's really lovely. But I believe that rests on the assumption that effectively you know the future, right? That the problem for parallelizing, say, an ODE integrator is that we don't know the future, so we can't parallelize it. Here, you know the future because the future is the past.
That's right.
And you have checkpoints of the future.
Yes.
But that relies on the assumption that the path each slice is going to trace through is really going to be the same. That every checkpoint you have is correct. And my question is, how do you control for that really key assumption to be respected in a world where, like, the data is being pulled from a database that may have been updated and you're not exactly sure that you're going to get the same things out, or GPU variability means numerics begins to drift, and then instead of this trustworthy path for the future, you end up with effectively like this mini multiverse breakup of these paths, and then that assumption is violated. How do you control for that?
Yeah. So if I can summarize, I feel like the question, I think one of the key pieces here is like, how do we ensure the like faithful reproducibility? Because if there's like branching cases, for example, you need to take the right branch every time. And if it was like a coin flip, a coin toss, how do you take that branch again? So that would be a challenge with like the instrumentation of the early chapter. I think we did make some assumptions about like what the deep learning structure looked like. But later with FloorDB, with the introduction of the API, that was the reason why we chose to include the floor arg. So if you have the floor arg in that branch, you could say like if floor.arg predicate, then that's going to get logged to disk and that's going to be available at replay. And so it's always going to take that same branch during replay. Same with like seeds, when you're initializing like scikit-learn models or PyTorch, for example, like the floor arg is going to make sure that the correct value from history gets read so that you're able to take that same path. And like, I know that reproducibility is important in machine learning. And so like folks at NVIDIA with like CUDA drivers and everything, like make optimizations to try, to make sure that if you're holding the seed correct, that this tree evaluation follows, the same order. But it's something to keep in mind. I think I would almost be curious or interested to like find those corner cases where like we don't take that right branch on replay. I think one of the cases would be like sources of non-determinism that we didn't know about, and so the more you try to guess that with floor arg, the better. Yeah, if there's additional sources, like I would be interested to find them.
One of the things that I think came up in your user survey was the idea that people don't necessarily know what the data in your organization means anymore over time. So I think there's some discussion of what's in this data set really and what columns mean what. You're generating more of that, right? In some sense, when you talk about things growing horizontally, you're saying, well, we can have more features. And every time I do onset logging, I might add another expression and generate another way of instrumenting what happened in the past. Have you thought about what it means to manage
that growing context? Yeah, I mean, I've kind of always leaned on the select, like select certain columns, and if there's some redundancy in the metadata, like I guess, yeah, it would accumulate almost monotonically, this context. So I probably don't think that the right answer is to like destroy any of that. I think it's fine for it to keep growing. I do think that like if the replication or the redundancy is too high, then it's a bad sign, because then like people are not understanding what's already there. And so then they're coming in and adding more stuff additionally. And so it's almost like the context isn't really like solving the problem. Like it's just kind of generating more stuff. It might be an issue of like managing like user space, like I think that the ABCs of context are like a very good rubric for making sure that you have all the metadata that you need. But like you might find that like I don't have all the build context that I need, or I might need some more change context. And so it's like I might also need to track who the user is, and then have like user namespaces in order to kind of like manage that. Because people could be like, well, show me what others have done, or then show me what only I did, and then like that might be one of the solutions. So it might be like that we need to find a little bit more fine-grained like build context or change context. Kaushik?
Very nice. Very nice. You mentioned there is adaptation. So you have already released the tool. So what kind of feedback are you getting in terms of application? Which people are interested? What changes are you going to make based on that feedback?
Sure. So I think like some of the early guidance that I had as like aspirations. I know Jonathan Riggin-Kelly was a professor at Berkeley earlier in my grad school years, and he's the creator of Halide. And I saw like the success that they had by integrating with Adobe. And so it's like, oh, well, you know, you had someone who was building in C++ versus someone who was building in Halide, and they were able to get better performance and less development time. There was also like Mesosphere with Twitter, who went out and like deployed these things in the field. So we have like, we've done some open source collaboration. Part of the reason why I was so excited about the work with the Epic Lab was because we got to work with like journalists from QED and lawyers from NACDL. And so here was the case where like, you tell me what you want to build, and then when I build it, I'm going to build it with Floor. And so that's a way for like, to get them using it, because like I'm building the work for them. And so we're kind of like growing that so that other students in the group work with Floor with like AI/ML. But I also wish to continue that. You know, I've expressed interest to folks at Dell. There's been some interest from open source contributors like G Research. You know, we've heard that like now that LLMs are so interesting and they're so large and they take so long to train, that like checkpointing stuff with low overhead is like becoming really interesting. So like NVIDIA might want to know how to take a fast checkpoint from a GPU. So that's definitely something that I wish to continue to push. In my postdoc at ASU, I would be interested in continuing to collaborate with lawyers and journalists to kind of continue to get that tool out.
So another related question, since you mentioned LLM, like how would these techniques work for even a small or 7B model or 1B model? Try to train such model with Flow and see what is you can debug it.
Yeah. So I've used like inference only models, so like Llama 2 inference only, and like that one fits. It's kind of like tight for the GPUs that I have access to. The bigger GPUs are very difficult to lease right now. So I think like I wish to continue exploring that. I think with LLMs, I see people using them more in like inference only. So I almost see them as like build context, where like you can take a crowd worker path, or you can take an LLM path, or you can take this other like ground truth label. So, and it might be an issue of scale too. So like distribution. So I think if you're managing like a cluster of GPUs and you're taking like checkpoints in there, I think that would definitely be like a separate paper, for example, because it's not currently the set of capabilities that we have. So if I can very quickly also like give some thanks to my family. So like we talked about build context, like lineage, you know, and so I care about roots. My grandfather, like I can trace my American roots to my grandfather, who was a citrus and cherry farm worker in Chico, California. And so he worked there several years. Later, when I was born in Southern California, my dad was working 2 jobs, one of which was at an optical components factory. So he was developing these like quartz pieces that go into like the scanners or the projectors. And so my dad did that throughout his whole life. And I remember it was like very long shifts. Later on, we moved to Arizona, where I started out in Arizona in high school. And when I graduated from high school, it was time to pick a school. And so I picked an in-state school because, you know, like in-state tuition is much better. And ASU was the best engineering and computer science school that I had access to. And so I went to ASU, and then very quickly I found an undergraduate research lab that I had success in. And I went to an academic conference in Chicago, and that was like kind of eye-opening. I was like, well, this is what I want to do for a job. You know, I want to stay in academia. I want to like go to grad school and all that kind of excitement. And so I graduated from ASU. Then finishing that, I came over and started over at Berkeley. So ASU was like launching off place, this like just a way to launch off into Berkeley and get all of these opportunities that I have. And I feel like now it's like almost closer to Chico in a way. It's like so close but so far at the same time. And so next, it's like closing the loop, you know, go back to Arizona and kind of like pay back some of that blessing, really, that I've had to come and get an education here at Berkeley. And so I wish to return to ASU for engineering. I also wish to like help with the undergraduate population there, to kind of like pass on that same benefit that I had, so that other Arizona undergraduates have access to, you know, this kind of like world-class training that I've been receiving. And also, you know, like for Joshua and for my wife and for my father-in-law and everyone who's like, I have so much family in Arizona, like I also look forward to all of that proximity and all of that support. So thanks to everyone. And Floor isn't just like, it doesn't just exist in slides. Like you can also pip install it, you know, so like try it. And if you have any comments or anything, open an issue on GitHub and like start using it.